topic is the difference between thermoplastics polymers and thermosetting polymers. So thermoplastics and thermosetting plastics. These are, thermoplastics. You should remember one thing. From the example, you can easily make the points. So, for example, I will take this as one example, polyethylene. Here, I will take phenol formaldehyde, or I will take nylon 66 as example. From the example, we can make easily the points. So, polyethylene, it's a double bonded monomer. That means thermoplastics monomers. And under this category, the monomer will undergo the addition polymerization reactions. On the other hand, here condensation reactions. Here double bond is compulsory. There functional groups are compulsory, isn't it? Amine and the carboxylic acids. So these plastics can be reshaped, remolded, whereas these plastics cannot be remolded, reshaped because of it's a network polymer with 3D network polymer. Okay, this will be soft, weak, and brittle. This will be hard, strong, and rigidity, higher rigidity. So these are all the common points. And during these reactions, there won't be any loss of molecular weight. Here there is a loss of molecular weight because there is a formation of byproduct. There is a no formation of byproduct. And this reaction is very fast because the radical mechanism, here it is a slow reaction, it's a chemical reactions, condensation reactions. These are all the common points. And we'll go one by one. Thermoplastics is formed by addition polymerization, whereas condensation polymerization takes place for thermosetting plastics. And monomers are bifunctional. Okay, that means what? Double bonded monomers. Here the monomers are polyfunctional. More than two functional groups are needed for one monomer. So you need two monomers, isn't it? Because it is a condensation mechanism. Two or above. They are long chain linear polymers with negligible cross links. Okay. They have a three-dimensional network structure with a number of cross links. That's why it's very hard. They have low molecular weight. They have high molecular weight. They are soft, brittle, and weak, hard and strong, and more brittle. Okay. They can be softened and reshaped and reused when you heat it and mold it. Okay. They cannot be softened and reshaped again and again for this thermosetting plastics. The best example is polyethylene, polystyrene, PVC, PVA, all the materials here. Phenol formaldehyde, urea formaldehyde, melamine formaldehyde, and nylon 66. Now we will go to the preparation of few individual polymers. The first one is the fundamental polyethylene. So we start with ethylene, we end up with polyethylene. What is ethylene? CH2 double bond CH2. So this N number of this unit is needed. So I'll put a bracket like this. This N stands for what? Degree of polymerization. Okay, this you should recall it. And the condition is 1000 atmosphere and 200 degrees Celsius, and traces of oxygen is needed. It will polymerize by free radical mechanism. There are two types of polythene materials. One is high density, other one is low density. Okay, high density polyethylene, low density polyethylene. What is high density polyethylene? What is low density polyethylene? So high density polyethylene is that has a minimal, I have given here, that has a minimal branches. Okay, which makes more rigid and less permeable than LDPE. Low density polyethylene has more extensive branching, resulting in less compact molecular structure. So this point many students will confuse, because generally what we think, more the branches, so more will be the rigidity. Okay, so more will be the rigidity. The term will come into our picture is high. High density means what? So that should have a more branches, but here it's not the case. So the lesser branches will give us a high density polymer, whereas more branches will give us a low density polythene. The arrangement of the monomer in the polymer, this tab, cellular tab. Okay, transparent cellular tab is nothing but low density polyethylene, and these packing materials to carry vegetables and all, we carry the polythene bags, that is made up of low density polyethylene. What is the polymer code here? 04. Okay, this is the polymer structure. High density polyethylene, remember, high density, so it means that can withstand more weight, isn't it? So for this thick cans, this bucket, dustbin, and this larger sized polythene bags are made up of high density polyethylene. What is the code here? Polymer code 02. So 02 is high density polyethylene, 04 is low density polyethylene. And also it is very much useful in other applications also. Helmet is made up of high density polyethylene, and gears in automobile industries, and joint replacements in medical field, medical surgery. If any damage in the knee, the doctor will fix it. This material, that is ultra high molecular weight polyethylene material, will be fixed for knee joint issues. Next one is polystyrene. Polystyrene or vinyl benzene. This group is called as vinyl group. This is benzene, isn't it? Or styrene. So you need to have a catalyst, that is benzyl peroxide, and you need to have an initiator, okay, and solvent and temperature. So when you heat that, the double bond will convert into a single bond, that is polystyrene. Okay. And properties, its density is 10 kg per m cube to 50 kg per m cube, and polystyrene used as a thermocol for preparing thermocol materials. Basically, it is a crystalline materials, and its specific gravity is 1.03 to 1.06. Density is 6.06 to 0.65. Water absorption capacity is 0.03 to 0.1%. And application point of view, so you know that the thermocols and what, milk bottles, pipes, and shopping bags. Okay. There are for other polymers also given here, but at this place only these two are enough. Low density polyethylene for polythene bags for carrying the food materials, vegetables. High density is used for bucket, larger size polythene bags. Next one is PVC. What is PVC? P stands for poly, V stands for vinyl, C stands for chloride, polyvinyl chloride. So vinyl, okay, this is vinyl chloride, CH2 double bond CHCl, but here it's a mistake. When it's polymerizing, you have to have the N here, and this double bond shouldn't be there. Okay. So like this also you can put here, nothing wrong. That means chain extends at the left side as well as at the right side. So this is the colorless material, but then you can ask me why these PVC pipes are, or covered for electrical wires are colored. Okay, So we add some additives to give us the color, but in general, PVC is a colorless powder. Okay. Preparation, how do you prepare it? From the monomer vinyl chloride. So vinyl chloride, how do you prepare it? To start with acetylene. This is acetylene. You treat with hydrochloric acid. You end up with vinyl chloride. Okay. This is acetylene. This is what? VC, vinyl chloride. Okay. So the production of the polymer PVC involves suspension and emulsion polymerization, where suspension has a major role. It is a linear polymer. It is a linear polymer. Okay, PVC. Properties. So the weathering stability, because of its rigidity, it can withstand high temperature. Versatility. PVC can be flexible and rigid. Fire protection. It is having the tendency to withstand high temperature because of the chlorine content. Longevity. So this PVC materials can last up to 100 years. Imagine up to 100 years. PVC pipes are not. It's not easy to worry about the stability. It's generally not necessary to worry about it unless we do any firing. These materials are very, very stable. And one more thing, PVC has high thermal power. High thermal power. When utilized in incinerators, PVC produces power and heat for home and industries. This is another point. So barrier properties, PVC can be made impervious to liquids and vapors. Recyclability, so PVC can be recycled because it comes under the thermoplastics. Economic efficiency, PVC is the cheapest polymer when compared to the other polymers. You can see here PVC for flooring in the indoor game stadiums, leather jackets, and also pipes and bedspread and all can be used for. They can be used. PVCs can be used. This is some other images of PVC materials. This is the formula, molecular formula of PVC. Next one is polypropylene. CH11CH, CH3 n times. Polymerization will give us a polypropene. This is in simple form P. This is polypropene. Okay. It's a linear polymer. So the main attractive features are that its exceptional flex life, good surface hardness, high chemical resistance, good stability in boiling water, excellent electrical conductivity, electrical property, long life integral, hinge applications. So this polypropene are of in three forms: isotactic form, syntactic form, adactic form. So compared to polyethylene, what is the advantage of these materials? Which material? Polypropene is that it has a lower density, it has a higher softening point and hence a higher maximum service temperature. So articles can withstand boiling water and can be subjected to steam sterilizing operations. It has a higher brittle point. It is more susceptible to oxidation. And the adactic polymer, what is adactic? The methyl groups are in random arrangements. It is amorphous in nature and rubbery in nature. Commercial polymer is usually 90 to 90% isotactic polymers, and the remaining residual is this one, syntactic and adactic. So general properties of this polypropylene, chemical properties. So no solvent affects the polypropylene at room temperature. That's very, very important. It's highly stable. Polypropylene will dissolve in decalin at 130 degrees Celsius. So you have to heat this polymer at 130 degree Celsius. Aromatic and chlorinated solvents often swell polymer at elevated temperature. This point is very, very important. So if you take this polymer and soak it in aromatic solvents or chlorinated solvents, not aromatic solvents, benzene, toluene. What do you mean by chlorinated solvents? DCM, chloroform, carbon tetrachloride. These are all chlorinated solvents. Okay. Aromatic solvents, benzene and toluene. So what happens? This polymer, if you put it in this material solvents, it will swell. Okay. Strong oxidizing acids slowly attach the resin. For example, if you put this polymer in the fuming nitric acids, it starts decomposing. Okay, because of the power of fuming nitric acids. Okay. Now the electrical properties. PP is an excellent insulator due to its non-polarity. It is used in many molded products as well as in winding coils and transformers. Okay. Now the flammability. Flammability is nothing but the tendency of the polymer to withstand at different temperatures. So polypropylene burns slowly and can be identified by an odor of crude oil. Flame retardant grades are available for specific electrical applications. Mechanical properties: when compared to polyethylene, polypropylene has higher mechanical properties. Applications: in automobile industry, it's very useful. So in bumpers, steering wheel covers, profiles, consoles, door pockets, radiator grills, spoilers, and rubbing strips. Okay, packaging. Polypropylene is used in packaging for goods, products, cosmetics, contact lenses, and first aid cases, drums. Okay, and this is also useful in electrical and electronics applications as cable connectors and fittings and wire coatings and industrial flights. There are some images of polypropylene polymers. The next one is PTFE. PTFE has another name, that is Teflon. You can see here Teflon. Teflon is nothing but polytetrafluoroethylene. How do you prepare that? You start with the monomer, that is N number of is the tetrafluoroethylene. Okay, you take the monomer and then you add a catalyst. What is the catalyst here? Peroxide. You add solvent and you add, sometimes you heat it, get the polymer. Actually, this polymer discovery was a serendipity by a DuPont company. Physical properties. I have given here some physical property. Melting point is 327 degrees Celsius. Glass transition temperature is 115 degrees Celsius. Crystallinity is 60 to 80%. Degradation temperature is 260 degree. Chemical resistance in aqua regia is very good. Even aqua regia also it is very stable. What is aqua regia? Aqua regia is nothing but hydrochloric acid, nitric acid mixture plus hydrochloric acid plus nitric acid mixture. Hydrochloric acid is 3 ratio. Nitric acid is a 1 ratio. Okay. Applications. You can see here Teflon. Teflon coated pan. We use it for making dosa and all. Non-stick tawa we used to say. And also corrosion resistance in steel industries. Okay, semiconductor industries we use this. And hair styling tools. These are all made up of Teflon materials. Okay, and this one Teflon tabs, coating materials are all nothing but high resistance, high rigid Teflon materials. These are all other important properties of a Teflon non-stick. Unique electrical properties, low coefficient of friction, cryogenic stability, no wetting, chemical resistance, heat resistance. Next one is polymethyl methacrylate. It's very important polymer. This polymer it will be used as a membrane in osmosis process, reverse osmosis process. The monomer is what? MMA. What is the MMA? Methyl methacrylate. That is the monomer name. When it polymerizes, polymethyl methacrylate. Understand? This is very simple. So, n number of these monomers will be taken, and it's a free radical mechanism. Free radical means same temperature, solvent, and one peroxide catalyst. Okay. So now physical properties and mechanical properties. Some important properties I have given here: refractive index, flammability, water absorption, and then radiation resistance, UV resistance, and density. Mechanical properties: stress, strain, Young modulus, tensile strength, elongation, compressive strength, Poisson ratio, hardness, stiffness, toughness. All the properties are given here. This is the material photo image. It looks like a crystal pieces of sugar moiety, colorless materials, and then this is also useful in the biomedical applications, cosmetics, diagnostics, dentistry, orthopedic, ophthalmology, drug delivery. So in these all biomedical applications also, this material is very much useful. Next, condensation polymerization. The first one is the nylon. It's a polyamide, nothing but polyamide. Polyamides are synthetic polymers having the common amide linkage. What is the common amide linkage? CONH group. That is the common amide linkage. So nylon has two derivatives: nylon 6,6 and nylon 6. Nylon. This is we discussed 2-3 slides back. This is the reaction. Starts with two different monomers, hexamethyldiamine and adipic acids. Adipic acid has 2 carboxylic acid. Hexamethyldiamine, that is NH2 group. These two will react. Here there is a OH, here there is a hydrogen. Water will be eliminated. What is the byproduct? Byproduct is water. So minus H2O. Okay, so we get the polymer, that is nylon 6,6. This bond is important, that is the amide bond. What do you mean by 6,6? 6,6 means the two different monomers, each monomer has a 6 carbon. It is like 6 carbon is to 6 carbons. Okay, see here. The first monomer, there are 6 carbons. The second monomer, here there is a 4 carbon, 4 methylene groups, and one carboxylic acid carbon, another carboxylic acid carbon. So totally 6 carbon. 6 carbon is present in this polymer. Properties of nylon polymer: it is a less soft and stiff material when compared to nylon 6. Its melting point is how much? 264 degree Celsius. Next one is nylon 6. Here only 6 is there because it's a single monomer with 6 carbons. Okay. So this is a caprolactam. This can be prepared from a single monomer. What is the monomer here? Monomer is nothing but this will be prepared by starting with CH2 5 times. In H2 and then COOH. So what happens? This is called as say a monomeric unit with one carboxylic acid or amine. Okay, and when you heat this monomer, this OH and this hydrogen will be eliminated. Okay, so elimination of the byproduct water, we get this caprolactam. Lactam on self-dissociation on heating, this ring will open, so you get this product. CO, C6 5 times, NH, N times. This is nylon 6. From this nylon 6 and nylon 6, you can easily understand which one will be having more melting point. Definitely nylon 6,6, because more the functional groups, more will be the amide bonds when compared to this nylon 6. Okay, so lightweight materials, comparatively less melting point when compared to nylon 6,6. General properties of nylon: they behave as plastics as well as fiber. They have both properties. They are translucent, white, horny, and high melting polymers. They are insoluble in common organic solvents. This is very, very important points. But soluble in phenol and formic acids. They possess good mechanical properties and fairly resistance to moisture. Now the mechanical properties: stress, strain, tensile strength, all the properties. They are characterized by combination of high strength, elasticity, toughness, and abrasion resistance. Nylon 6 is used for fibers which are used in making socks, ladies' shoes, dresses, and carpets. Nylon 6 is mainly used for molding purposes for gears, bearings, electrical mountings, etc. Nylon bearing work without any lubrication. Nylons are used for making filaments of rope, bristles for toothbrushes, films, and tire cords. So images of nylon rope. So the fish rods is nothing but made up of nylon materials. It will be like this: nylon materials, nylon cloths. The next one is formation of polyester. Formation of polyester. What is ester? This group is called as ester group. CO. How do you get that? You get the ester from the reaction between the acid group and alcohol group. These both will react when you heat it. What is the byproduct here? Water is the byproduct. So minus H2O I will write here. So what is this? This is dicarboxylic acid. And dihydroxy compounds. The elimination of water molecules, we get the polyester. Another polymer is terylene. It's another interesting polymer. Terylene. So what are the monomers here used for the preparation of this? Phthalic acid and ethylene glycol. Ethylene glycol. This is phthalic acid. What you do, just heat it. With the elimination of water molecule, you end up with the ester link. Okay, it is called as terylene. Another polymer where instead of a carboxylic acid, it is a OCH3. Okay, substituted phthalic acid. Here also OCH3 substituted phthalic acid. What happens when it reacts with ethylene glycol? Here methanol will be eliminated. What is the byproduct here? Methanol will be eliminated. We end up with a polymer that is dimethylbenzene 1,4-dicarboxylic acid. So polymer. So because of the bulky groups, it is more rigid than aliphatic substituted polyesters. Next one is Teflon. This PET powder. What is the full name? Polyethylene terephthalate. So this is the polymer. How do we get that? Terephthalic acid and ethylene glycol. This is ethylene glycol. This is terephthalic acid. I said phthalic acid earlier. It's not phthalic acid. It is terephthalic acid. This one. Terephthalic acid. Okay. Phthalic acid means 2OH group at the ortho position. Here 2OH group is at the para position. That is terephthalic acids. When these two are reacting, which two are terephthalic acid and ethylene glycol? With the elimination of water molecule, we get the ester, that is polyethylene terephthalate. We call this water bottle as PET bottles. PET is nothing but polyethylene terephthalate materials. So one thing we should know that these bottles are not good for carrying the hot water above 40 degrees Celsius. So this ester bond is very weak. That will kill you. We store this bottle with hot water. So always you have to use the cold water only. And Kevlar. Kevlar is another polymer which is used for bulletproof jackets. You can see here, in both monomers, the bulky groups are introduced. Here, what are the two monomers? One monomer you can easily see here. One monomer is this amine monomer. Another monomer is this acid monomer. That means one aromatic compound with two carboxylic acid at the para position and another aromatic compound with the two amine at the para position. So I write like this. You put phenyl group, put ring, take carboxylic acid, substituted aromatic compounds. What is the name of this group? This compound? Terephthalic acid. Okay. You put another monomer. Aliphatic generally will have lesser rigidity. So we go for aromatic with NH2 group, phenyl group. These two will react with the heating. What happens here? OH and here H will be eliminated. So minus water molecule. You get the amide bond like this. That is the amide bond. The CONH amide bond. CONH. Understand? So this is a strong network and hot material for due to the covalent bonds. This will be used as a bulletproof jackets. Some examples of these Kevlar materials.